Hello. In this video, we're going to look at the mean value theorem. Well, we're actually going to look at the precursor to the mean value theorem, Rolle's theorem, and hopefully in the next video we'll be able to cover the mean value theorem in full. And for right now, we want to start with our motivation, which is related to the problems that we did earlier. Does this graph right here, does this graph have a derivative of 0? Or in other words, does it have a horizontal tangent line? And if you look, I'd say right about there, it looks like we'd have ourselves a horizontal tangent line. Yeah, we have a derivative of 0 there. But does every graph have this happen? Does every graph have a derivative of 0 somewhere? And of course the answer would be no, right? I could draw a graph like this, just a nice straight line. That's got a derivative of 0 nowhere. It doesn't have to have a derivative of 0 somewhere. But if we have a certain set of conditions, then this would be true. And what are the conditions we need to eventually make this happen? Well, looking back at the graph we started with, it clearly has the same y value on the endpoints. It starts and ends in the same place. So we have the same y value at the endpoints. We also notice, of course, that the graph is connected. It's continuous. And it is also differentiable. And in fact, if you have those three conditions, you can prove that the graph will always have a derivative of 0 somewhere. And this was discovered by someone named Rolle, so it's called Rolle's theorem. So here's the theorem. Let fx be a continuous function on the closed interval ab, differentiable on the open interval ab, such that f of a equals f of b. This is saying that the two endpoints have the same y value. Well, if that's true, then there is at least one number c in ab such that f prime of c is equal to 0. So let's go ahead and look at the proof. So step 1, we actually have to consider 3 different cases. So case 1 is we're going to suppose f of x is a constant function. So f of x just equals k, where k is constant. Well, what happens to the derivative then? Well, f prime of x is equal to 0 for all x in the interval a to b. Right? The derivative is 0 everywhere. So we can then pick any c. So pick any c. And f prime of c is equal to 0. That's a bit of a boring case. If you have a constant function, a flat line, well, the derivative is 0 everywhere. So, of course, we have a derivative of 0 somewhere. But we need to get that case out of the way so we can do case 2 and 3. So for case 2, now we're going to suppose that the function is not constant. Well, if the function is not constant, either the function goes up or the function goes down. Because, well, those are the only two directions you can go. You can either go up or go down. So we're going to start with case 2, and we're going to suppose that f of x is greater than f of a for some x in the interval a to b. So suppose that the function goes up from the endpoint. Well, by the extreme value theorem, we know that fx has a maximum value somewhere in AB. Somewhere in the interval a to b. Now, we know that the interval a to b has endpoints that are equal, because that's part of the assumption. So we could say, since f of x is greater than f of a, which is equal to f of b. Right? If it goes up from the left endpoint, clearly that's going to be higher than the right endpoint. So what this means is that the graph goes up, and it has a maximum. So this maximum value is not at the endpoints. That's the key right here. The maximum value cannot be at one of the endpoints. So since f of x is greater than f of a equal to f of b, it must attain this maximum value at a number c in the open interval a to b. So the maximum value cannot be happening at the endpoints, which means it happens somewhere in the middle. So it happens somewhere on the interval a to b. But if the maximum value is happening in an open interval, it's not just the absolute maximum. It's also a local maximum. So, thus, fx has a local maximum at c. Okay, so we found this maximum, and apparently it's a local maximum. Why is that so important? Well, if you have a local maximum, you are in the realm of Fermat's theorem. Because if you remember from Fermat's theorem, anytime you have a local maximum, what has to happen? Well, the derivative has to be 0. Well, technically, the derivative either has to exist, and then the derivative has to be 0. But because we've assumed the function is differentiable, we know the derivative exists already. So if the derivative exists, which we know it does, the only option for the derivative is 0. So we would say, thus fx has a local maximum at c, and by Fermat's theorem, f prime of c is equal to 0. Well, there you go. You just found yourself a place where the derivative is equal to 0. Case 3. So case 3 is exactly the same as case 2. It's just that we're going to suppose that f of x is less than f of a for some x in the interval a to b. So now we suppose that the graph goes down. Again, by the extreme value theorem, we know that fx has a minimum value. Somewhere in AB. And since the function goes down, since f of x is less than f of a equal to f of b, it must attain this minimum value So it must attain this minimum value at a number c in the open interval a to b. Thus, f of x has a local minimum. Because if you have a minimum value in an open interval, it's not just a regular minimum, it's a local minimum. So thus fx has a local minimum at c. And by Fermat's theorem, by Fermat's theorem, f prime of c is equal to 0. And there's the end of our proof. So let's do a quick multiple choice question. Which of the following is not a hypothesis of Rolle's theorem? So remember, hypothesis means the beginning, the first part of the theorem. So which is not a hypothesis? Pause the video and give it a try. Alright, so let's look here. Hypothesis. Hypothesis means we're looking at the beginning part. Well, f of x is continuous. Well, that's definitely one of the hypotheses, so we need that. F of a equals f of b, we need that. Differentiable, we need that. Oh, f prime c equals 0. This is not part of the hypothesis. This is the conclusion of the theorem. So the answer would be C. So let's try an application of Rolle's theorem. Let's look at this function, x cubed minus 12x, defined on the interval 0 to 2 root 3. Let's show that it satisfies Rolle's theorem. So the first thing we should check, of course, is the endpoints. So we could check f of a. So f of 0, which would be equal to 0 cubed minus 12 times 0. So just 0, okay? And we'll check f of b. So f of 2 root 3. So we'd have 2 root 3 cubed minus 12 times 2 root 3. That's a little nasty. Well, 2 times root 3 cubed, we could cube both of those. So 2 cubed will be 8. And then we'd have root 3 cubed, I guess, minus 24 roots of 3. Well, if you're going to cube a root of 3, that means you've got root 3 times root 3 times root 3. So 2 of those root 3's can be combined to make a 3, and then you've still got another root 3. Well, 8 times 3 is 24, so you've got 24 roots of 3 minus 24 roots of 3. Yep, you got 0. So f of a equals f of b, that's true. Is fx continuous? Well, it's a polynomial. We proved that polynomials are continuous, so yeah, it's continuous. Is it differentiable? Of course, it's a polynomial. You can always take derivatives of polynomials. They're nice and smooth. So we would just state f of x is clearly continuous on the interval 0 to 2 root 3, and f of x is clearly differentiable on 0 to 2 root 3. Okay, now this shows that the function would satisfy Rolle's theorem. And so we could then say, because Rolle's theorem is a true fact about math, we could just say, therefore there exists an f prime c such that f prime of c equals 0. Yeah, we're going to have a horizontal tangent line. It's guaranteed. But the theorem, I should say, doesn't tell you where the function has this 0. It just tells you that it exists. It's what's called in math an existence theorem. We know that it exists, but where is it? And so we're actually going to go ahead and find it, because it's kind of fun. We can find where the c is. We know we're going to find one because of the theorem, but let's try to find one. So let's find the derivative, which will be 3x squared minus 12. And let's go ahead and set that equal to 0. So you'd factor out the 3, x squared minus 4. Do a little difference of squares, x minus 2, x plus 2. So you get x equals to 2 and x equals to negative 2. Well, of course, we have to reject the negative 2 because that's not in the domain. So we reject this. But x equals to 2, is that part of the domain? Well, you think about it, 2 times root 3 is clearly going to be greater than 2, because root 3 is about 1 point something. So yeah, this is definitely in the domain. So we can see very clearly that f prime of 2 is equal to 0. You could even try if you wanted, right? Plug this back in here. 2 squared is 4, 3 times 4 is 12, 12 minus 12 is 0. So f prime of 2 is equal to 0, definitely. And 2 is an element of the interval 0 to 2 root 3. It's in the interval from 0 to 2 root 3, so it's our c that we're looking for. So that's nice. We found our c, and we could say this verifies Rolle's theorem. This verifies Rolle's theorem. I mean, Rolle didn't really need us to verify his theorem. He proved it. It's true. He doesn't need us to show that it's true. He already did that. That's why he got the theorem named after him. But it's nice for us to verify it so that we can believe it. Now, we're going to go ahead and show this example on Desmos and then give a bit of an analogy to really make sure we understand what's going on here. So here we have the function graphed on Desmos. We can clearly see the two endpoints are both the same y value. We can see that the function is definitely connected, it's continuous, and it's differentiable, it's nice and smooth. And if we check that point right there, sure enough, at x equals to 2, we have a horizontal tangent line. So all the pieces of Rolle's theorem can be nice and visualized right here on Desmos. Now, let's think about a bit of an analogy here in terms of how you could visualize what's going on here in a physical sense. So let's say we had ourselves a little graph. Let's say it was, maybe distance versus time, position versus time. So x versus t. And let's say that you're on a line. So here's you. Hopefully you're happy. And you're going to run back and forth on this straight line. So let's say you started right here, and you moved forward for a while, so you went this way, and then you decided you wanted to come back, back here. Well, you would have started at some position here. You would have gone away from that position, so your x value would have increased, and then you would have come back to where you started. It's like you're running on the line, so you run away and then you end up back where you started. Well, if you were to run away and then come back where you started, in that process, imagine yourself as you're running this way and then you go to turn around and come back. At some point, I don't know where, you're in charge of the running, you're doing whatever you want, but at some point, you have to turn around and come back. And when you turn around, when you go to return this direction, when you make that little pivot there, at that point, wouldn't you agree that your speed was 0? That as you turned around, you had a velocity of 0 at that point? I mean, surely that's what it means to turn around, right? Instead of moving forwards, you're moving backwards, and there's that instant where you're not moving at all. And so at that point, you had to have a speed of 0. And the derivative of position, of course, is speed. So here, we definitely had to have a speed of 0. So that's a way of thinking about it, an analogy. If you run around and end back where you started, at some point along the journey you had to turn around, or at some point your speed had to be 0, and that's a physical representation of what Rolle proved in his theorem. So which one of these functions would not satisfy Rolle's theorem? Go ahead and pause the video, give it a try. Okay, so let's look at them one at a time. We should probably check the endpoints. So sine of 0 is 0, which is actually sine of pi. And sine is continuous and differentiable, so that should satisfy Rolle's theorem. What about x squared plus 3x? Well, negative 3 squared, that's going to be equal to 9. So 9 minus, well, that'll be 9 minus 9, so that'll be 0. And if you check the other endpoint, that'll be 0. And that's a polynomial, continuous, differentiable, yep. Over here we've got a straight line. Well, the derivative is always 0 for that. That was case 1, so that's clearly true. In this case, we've got 5 equal to 5. The endpoints don't have to be 0, by the way. They just have to be the same value. For tan, we could check the endpoints. Tan of 0 is 0. And tan of pi is also 0, so the endpoints are good. Tan is continuous and differentiable, but only within the interval of its periodicity. As tan goes from minus pi by 2 to pi by 2, it's continuous and differentiable. But then you've got that asymptote right there, and it is not continuous at pi by 2 until it picks up again for the next period. So tan is not continuous on this interval, which means Rolle's theorem does not apply. Now, we're going to want to eventually prove the mean value theorem. And to do that, we're going to use Rolle's theorem and some interesting information about tangent lines and secant lines, but we've got to be a little bit precise first. And so before we actually look at the mean value theorem, which we'll probably do in the next video, we need to define a tangent line and a secant line so that you can at least work with these concepts. So a tangent line, which hopefully you've gotten really familiar with, is just like this. It touches the graph at one point and it's got the same slope as the graph right there. It just glances off the graph. But a secant line is where you take the first point and the last point, the two endpoints, and you draw a line connecting them. That's called a secant line. Now, the tangent line slope, we know the slope of the tangent line will just be the derivative. But the secant line slope is a little bit different. You might have to say, okay, well, there's going to be a point over here at b and f of b. And there's a point over here at a f of a. Well, I can use my slope formula. We would do y2 minus y1 over x2 minus x1. So the secant line will have slope f of b minus f of a over b minus a, because it's y2, y1, x2, and x1. So that's going to be the slope of the secant line. Now let's go ahead and actually try to find an equation for the secant line. Well, we know that an equation for any line would be y minus y1 equals m x minus x1. That's our go-to point slope formula for a line. So for the secant line, I'm going to use the first point. So y minus y1, I'm going to use f of a, equals m, which we know as f of b minus f of a over b minus a, and then x minus a. Now I know that's a bit of a crazy formula, but if we move the f of a to the other side, we have the following. Y equals f of a plus f of b minus f of a over b minus a times x minus a. It's a big equation, but this is the equation for a secant line. Of course, you need to have the endpoints, and you need to have the original graph. You need a function for that. But if you're given a function and you're given the endpoints, you can write this down, and you'll come up with an equation for the secant line, which, by the way, is helpful if you're trying to graph it on Desmos. Now, we're going to look at another function, though. We're going to consider a function g of x, which is going to be defined to be the distance between the function and the secant line. What I mean by that is if we look back over here, we have the secant line and we have the overall function. And what I want to do is I want to measure this distance right here. I want to measure this vertical distance between the function and its secant line. I want to measure how different they are. What's the gap between the function and the secant line? And of course it's going to be different, right? It's pretty big over there near the very end. Looks like that distance is a lot smaller. And I want to measure that distance somehow. Well, if you remember back to pre-cal, there's a function operation we can use to measure vertical distance. The way we measure the vertical distance between two functions is we subtract them. So what we're going to do is we're going to take f of x, and we're going to take the secant line, and we're going to subtract the two functions. We're going to call this thing a new function. In pre-cal, you would have called this like f minus g or something. But here we're just going to call it g of x. So g of x is going to be equal to f of x minus the secant line. So f of a plus f of b minus f of a over b minus a times x minus a. I know this is getting pretty crazy, but we're just going to go ahead and expand out those negatives, and we'll get our final g of x. So g of x is equal to f of x minus f of a minus, because we've got to distribute that negative, f of b minus f of a over b minus a times x minus a. Okay, this is the function that measures the distance between the original function and the secant line. Now let's look on Desmos to try to understand what's going on here. We're going to look at a concrete example to see how these functions work. So here we have the function in red. Here's our f of x. And we've drawn the secant line, which goes from the first point to the last point. It goes from the two endpoints and connects them. And if you notice, initially, the function and the secant line are actually at the same point. So the distance between them starts off at 0. But then as they go, they separate, and if you notice, they begin to become really separated somewhere along the middle here. And then eventually they get closer and closer and closer and closer, and they go back to being at the same point. So when we graph that, we get this purple function, g of x, which is the distance between them. You can see here they've got a bit of distance, so that's the graph there. Here they got a lot of distance, there's the graph there. A little bit of distance, there's the graph there. So the purple graph is measuring that vertical distance. Again, this is quite involved. We're having to create a secant line, we're having to create this g of x. But together, these concepts are going to allow us to create the mean value theorem. So a quick multiple choice question for you here. Which of the following blue lines is a secant line? So pause the video, give it your best shot. Alright, so clearly A is a tangent line, not a secant line. B might be a tangent line. B looks a little bit weird though, so definitely not B. I don't know what C is doing. But if you look at D, it's going from one endpoint to the other endpoint and connecting them. That is definitely a secant line. So in the next video, we'll combine these ideas to state and prove the mean value theorem. But until then, make sure you try some homework on page 292, number 5 through 10. Thanks for watching.